for the introduction. Let me just share the screen. All right. Can you see the slides? Just can you confirm it to me?
You can see it. Perfect.
Cool. All right. So hello, everybody. Thanks again for the introduction. So I'm Alex, and today I'm going to speak about mathematics of machine learning. In fact, this topic is quite vast, in my opinion. So I won't be able to cover all the mathematics which can be used in machine learning, but I will try to cover some parts which I think are quite essential to understand what's going on in machine learning. So thanks again for the introduction. I think I have basically nothing to add to that. So the plan for today is the following. I'm going to cover just very quickly what is the regression problem in machine learning, and then which will be kind of used as a motivational example. Why would you need to use some of the mathematics which you need to know for machine learning? Then I'm gonna quickly cover the concept of the function and why do we need that. Then a gradient of the function or function derivative. It's an object which quantifies how does the function change, which is quite important to use in machine learning because it will give rise to such algorithms as gradient descent or a more practical variant as stochastic gradient descent. Using these algorithms, you can solve some of machine learning problems. Voila, so let's just start. Let's start from functions. So let's start from the already a practical problem. Let's assume that you have a house prediction problem, house price prediction problem. So you have some houses of different sizes. They can be like measured in the surface of the house. How many square meters do you have? And your objective is to basically predict the price of an associated house. In other words, you want to have something which is called F, which for a given house will give you a price of this house. We may call it a function. It will be something which relates a house to its price or house size to its price. So it's something which can describe the relationship between two sets, which are sizes and the prices. You can also look at this as a regression problem. So here I have a data set containing X and Y's, where X axis corresponds to the house size, so how many square meters in the house we have, and Y corresponds to the price of this house. So we can basically pull over this data set from some maybe public database and have these pairs, and we can draw them as points on this graph. And basically what we want is to find such a function, so something which relates the axes, which are house sizes, to the prices, which are Y's in this case. It should not be ideally we want it to be equal to Y, but maybe it's not always possible to make it equal. So we want it to be kind of close to the Y's we observed in the data set. Obviously, if you put F such that it for every house size, it just gives a price of 0, it's kind of not an interesting function in some sense. We kind of understand that. It also needs to be able to predict, in this case, predict the points which we didn't observe in the data set. So the red dots on this graph. So it has to perform well in some sense. So it have to be close to the values which we observe, which are these blue lines, and also to the houses which we didn't observe, because we want to use this object, this function, later on to like predict the house prices and maybe use it to our own advantage. Maybe by, I don't know, if we are a real estate agent, we want to price the houses. So if you think about like what kind of functions we can draw here, it can be, there could be multiple choices. It can be like a straight line like this, which basically for a given x will give you a value which is associated and lies on this line. It can be a more complicated function like that. But basically our objective is just to have a function which will do this job of, for a given x, which is house size, give us a price of this house. So this problem can be formulated as a regression problem by basically saying that we want to minimize this objective, where in this objective, what I basically express is just the closeness of the predicted value by the function. So f of xi is something which my function gives, and the y, which was a value which was observed in the data set. We want, like, this symbol here means the norm, but you can basically, in this case, consider it as brackets, just brackets, and this difference is squared. So I will not really explain why we want a square difference in this case, but this can be used as a reasonable metric. So something which can measure how good job we do by predicting the values on this function. And we want it to be kind of summed over the whole points in our data set. And then, so if you have this kind of objective, you want to find the best possible function. So you kind of want to minimize it over all the kind of functions which are looking on. So just examples of some functions which we typically encounter in mathematics and in this talk as well. So first is linear function, which is basically like, it can be equal, so f of x for a given x give you just the x. So it's linear because it's kind of a line, you see, it's just a line. It can also have a different, inclination, so different angle at which this line goes up and down. There could be a quadratic function. Quadratic, it's called because we have a degree of 2 here. It basically is some, like, a bit more powerful function in some sense. But basically, there could be multiple choice functions, and these are two functions which we'll consider in this talk. Just to summarize, the functions are objects which can express a dependence between different sets of semantically different things, such as like house size and house price. And also, moreover, they can be used to make predictions about some unseen data. In case of regression, if you just think about mathematics, you can still approximate functions with some other functions and make kind of get the values for the axis which you care about. Moreover, on top of all of that, functions actually quite fundamental mathematical objects. They're used all over the place in mathematics. There is even a field called functional analysis, which just studies only the functions. So I believe you right now see the importance of using functions. So right now, once we have functions, let's kind of try to study the following topic. So if we have functions, can we quantify how does a function change? And later on, I will explain why do we need that in terms of solving an applicational problem. But right now, let's just look into this question. So let's look at these two functions. Here, the blue line corresponds to this to the quadratic function, so x squared. And the orange line corresponds to the linear function. So we have these two graphs. And you see they're kind of different, right? So one is kind of goes faster up than the other. It's strange why it is the case. So, and also we see that just for a different number of kind of similar number of x, it's kind of similar at the beginning, and then it's very different later on. So can we kind of understand what's going on and quantify this change? So let's look closer at this problem. Just, I think, an interesting observation. So let's take 2 points, x1 equal to 1 and x2 equal to 2, and just look at the associated values of the functions. And let's just take this difference, basically the size of this segment here. And because it's a linear function, and if we just take the difference of f of x2 minus f of x1, it will be just 1. So the difference here is 1. Then if we take points x equal to 3 and 4, and look at the difference here, it's also 1. So you see, you take 2 different points, but the distance between the points is 1, and distance between the values remains 1. So the change kind of remained constant. If you think about quantifying the change, you see, okay, this stays constant. This is quite an important information. However, let's look at the blue function. So if we take x1 equal to 1, x2 equal to 2, take the values, we see that the difference here, so I do the math for you, it will be x2 times x2, it's like basically 2 times 2, it's 4, minus 1 is equal to 3. So the difference here, this like the size of the segment is 3. But if we take the values at point 3 and 4, and look at the difference here, it's even bigger, it's 7. You see, like just the size of this segment increases. So you see, for the for the same set of points, one function gives you the constant change. So if you take the points at the same distance from each other and look at the difference of the values, the difference always remains the same. But here, in terms for the case of the blue function, the difference actually grows when we move x to the right. So why is this the case that one function has this property and the other function has the other property? And basically there is a concept which allows us to describe why one function changes in one way, in the other function it changes in a different way. And this is called the function derivative, or a gradient. Let me try to explain you how do we actually come up with the definition of the graph. So let's look at this function, which is basically a quadratic function. So x squared, or x times x. And let's put some 2 points on the graph of this function. So x1, x2. We don't care what are they equal to, just some two points on the graph of this function. Let's look at the associated values. So we have x1, f of x1, x2, f of x2. And let's just, I want to denote as b. B is just the difference between the values. And a is a difference between the x's. So I didn't do anything here on top of what I've done before. I just denoted these two terms as b and a. And you see here we have some kind of a triangle, right, emerging. So I will draw this triangle. So we have this triangle, and they have this violet line connecting basically this point and this point. And we have some kind of angle alpha, which appears. So right now, let's just look at the trigonometry. Let's just forget about all the graph. Let's just look at this triangle. And we know from trigonometry that tangents of alpha, so it's denoted as tj of alpha. I mean, I'm not sure if you know that. If you don't, I will add the links to the Wikipedia where you can take a look at why is it the case. But let's assume that we know that. So basically, tangents of alpha is defined as the relationship of beta over alpha over a, so b over a, sorry. And let's just, so we have this definition of tangents of alpha. we can rewrite this definition by just, rewriting b and a. So tangents of alpha is equal to f of x2 minus f of x1 divided by x2 minus x1. Right now, let's just rearrange the terms here, and we basically have that f of x2 is equal to f of x1 plus tangents of alpha times x2 minus x1. So if you think like just think about it, what is written here, we wanted to quantify how does the function change between the 2 points, right? And here we basically define how does it change. So if we know the value of function of at x1, so f of x1, we know x2, just the point of x2, and we know this tangents of alpha, we can know the value of f of x2. So in some form, we're already quantifying the change of function f, because we know the value in some different point. However, there is a problem here that this tangents alpha is kind of a complicated object to work with, because you see how it's defined. It's basically you take the two functions, you build this very complicated triangle. It's a mess to deal with. And it also depends on x2 and x1. So imagine if you wanted to look at how does the function change between, say, x3, x4, bunch of different points. Do you need to always construct this figure all the time? I mean, this sounds very complicated. So can we actually get a better job here and have a more compact object to work with? Before we go to construction of this compact object, let me just show you a few examples. So let's just look at the tangents alphas for the functions which we already know. So if you look at the linear function, so f of x is equal to x, it's a linear function, but if you just multiply it by some constant b, which doesn't depend on x, it still is linear function. It's kind of will basically define the slope of the line, or like the angle between the axis x and how does the line go up. So higher beta will correspond, higher value of b will correspond to functions which will grow very quickly. So if we just look at the tangents alpha, we take any 2 points and we just look at the definition here, we just plug this function into this definition, we basically obtain the tangents of alpha is equal to b. So if it's just f of x is equal to x, as b is equal to 1, and you remember we saw that the change between any 2 consecutive points was constant, was equal to 1 in that case. Here it would be equal to b. So it's kind of consistent to what we've already seen, which is good. Right now, if we try to look into quadratic function, so quadratic function again is basically f of x is equal to x squared. I plugged the definition of f of this function in the tangents of alpha. Then I just rearrange this first term here using this mathematical formula, and I obtain this tangents of alpha between any 2 points x1 and x2 is equal to x2 plus x1. So it's already not bad. It's not that complicated, but still it is something which depends on 2 points. So right now we'll see how to make it kind of more compact and more elegant, so it doesn't depend on 2 points. So let's come back to this picture. Let's right now do the following trick. Let's just put x1 and x2 closer to each other. So what we just did is we put the points x1 and x2 to be very close. You see one thing which is interesting, which appears here. You see that this violet line almost matches with the blue line, and it should not, right? Because the blue line is it's not a linear function. It's not a line. It's kind of, it's a curve which goes up. But if you put the points very close together, it almost matches with this violet line. So basically, you can think about is that if you know everything about the function at the point x1, so you know the value of the function of x1, you know exactly this kind of how to quantify this line, you can also obtain the value at x2. So it's kind of cool property, right? But right now, let's just say that x2 is equal to x1 plus some delta. So we just basically rewrite the definition of x2. We just say that it's x1 plus some delta, and we want this delta to be small. So we want the points to be small to each other, to be very close to each other. So if we just rewrite the definition of this tangents, you remember it was f of x2 minus f of x1. So I just replaced x2 by this definition. And it was x2 minus x1. And I also replaced x2 by x1 plus delta minus x1. So we just obtained that. So, I mean, we didn't really do anything here. We just rewrite the same thing which we had before. But right now, let's do this magical mathematical trick and just say that this delta is not just small, it's like extremely small. In fact, we will say that it kind of is infinitely small. So delta is not zero, but it kind of, we say it goes to zero. So it's like whatever small number you imagine, which is like still more than zero, like, I don't know, minus, 0.0001. So delta will be smaller than this number. It will be smaller than any number, which is positive, but it will be basically, it's like a mathematical way to say that delta kind of goes to zero. And you see that if it's the case, these points actually go so close that it's almost the same point. So x2 will be almost equal to x1. It will be like all this figure will become like a 1 point. And basically, in mathematical terms, the fact that something goes to zero can be expressed via a definition of a limit. So if you don't know what the limit is, I invite you to read about it in some calculus books. I don't really have much time to go for the definition of the limit. I think it's a very important concept to understand, because if you know that, you can do a lot of calculus, generally speaking. But basically, think about it as, if you have the function here under the limit, you calculate the value of this function of this delta. So the delta here goes to zero. If you divide by zero, if you divide by something small, the result will be very big. So if, for example, here at the top, it would have been, say, a constant. So say, imagine this difference is equal to 1. Then you will be dividing 1 by something which goes to 0, and it will be, result will be infinity. It's weird to divide by 0, right? So, but the way it works is because you actually have the value of a function as well, which depends on delta, and the function itself will kind of be expressed in terms of this delta, as you will see later. And that's why it kind of will cancel out actually, and you'll basically obtain something which actually depends only on the value of x1, because you bring things very close to each other and it's almost the same point. So there is no x2 here. It will be basically almost as we define this tangents at 1 point instead of 2 points. So, and basically this is what it would be if you do this trick of constructing this picture and basically collapsing the point x2 to x1, you'll actually get what we call a derivative. So the derivative is defined as the limit of this expression. If you don't like this expression, you can also look at this picture, look at this line, look at this point, at this green point, and we draw the line from this green point, this violet line. And this violet line is actually orthogonal. So the angle between, if you just look at this line between violet line, the blue line, and this like dotted line is 90 degrees. And what it means is that this like violet line is actually something we call tangent to the function. So if you draw a function and you at each point you can just draw the line which intersects this point at one, like intersects this graph at one point, and it's actually like, you know, parallel to like to the direction of your function in this point, and it will be perpendicular to, you know, if you draw the perpendicular through like this, like perpendicular line through a function, it will have a 90 degrees angle here as well as your function. So this is kind of another way to think about the derivative. So you have this like, you know, the line which we draw, but the derivative, as you remember, it's a tangent of alpha. So what you will have to do if you want to draw the derivative, you just draw the function, draw this violet line, and look at this angle alpha here. And this angle is basically defined between this line and the x-axis. It's just here, it's for convenience, but actually you'll put alpha, you can put alpha here. Another way to look at the derivative is that, okay, let's assume that delta is not zero, but it's almost zero. So if it's almost zero, and you just kind of rearrange the terms of this limit equation, but you don't go to the limit yet, so delta is almost zero. In this case, what we can say that the value of your function in the new point, which is like very close to your x1, it's extremely close, it's almost the value of the function at x1 plus this delta times this derivative. So the derivative often is described just as a speed of change of function. So, and if you think about it, it's kind of similar to what would happen in mechanics. Like, for example, if you drive a car, you know, at some point t, right, at some point in space right now, you drive for you push the gas, you know, your speed increases, and you drive to the next point, and you kind of compare these 2 points. You compare the time between 2 points, so you know the time, for example, you know how much you moved, and basically like this difference will correspond to the speed. And it will actually be described, if you like look at the mechanics, to a very similar equation. Just the trajectory time t will be equal to trajectory on previous time step plus the speed in previous time step times what we call delta t. Delta t is basically a small time interval which will elapse between t and t minus 1. Also, this is like in mechanics, often you have a concept. Yes, I see that someone raised hand. Please, how can I give hope? Just sorry, I didn't really. I'm not sure. So I don't know how to give the. Okay, allowed to talk. Voila, I allowed to talk.
Julius, you can carry on.
I think you might. Oh, wait.
Julius, your microphone is on mute. Please, you can unmute and you talk. Julius?
Okay.
Okay, so I don't know why it doesn't work. Let me carry on. There is still a few things to cover. Just, you know, feel free to write your question in the chat and I can look into that. And also at the end of the talk, you can ask me questions if you have some time. Voila. Okay. So just feel free to write the question in the chat. I will try to answer it. So let me just hide it. Okay, so just to summarize, right now we actually defined the derivative. So something which quantifies how does the function change. It only is defined by one point. So you look at the point x1, and you can define in this same point, how does the function change? In fact, this derivative is actually also a function. So you can even look at this function without looking into the previous function from which it is derived. So this is pretty nice. And basically, if you just want to summarize it in a few words, this derivative basically defines how does the function change locally, because we have this delta, which is very small. We just only look in a very, very small distance from your points. But if you know how does the function change locally, you can say a lot of things about how does the function behave in general, because you kind of can start to extrapolate from this like local to more global behavior. Also, just one thing to say is that because the derivative is the tangents of this alpha, tangents actually can take any value from -infinity to +infinity. It means that it's not really in any way limiting definition. So it doesn't, prevent us to express a lot of functions. And it's also a very compact way. So compared to just looking at two points, and describing the change between the 2 points, we look only at 1 point, which is very cool. All right, so if we just remember, we expressed this tangents between 2 points for our 2 functions which we looked at. Let's try to write a derivative for these ones. So for the first function, it will be the same. If you just write the definition of that, you write the equation, and it will be equal to b. So it's good that we get the consistent result if we look at the different, definitions of how to quantify the change for the same function. And for the quadratic, we had something which we call tangents of alpha, it was equal to x2 plus x1. But right now, if we define it in terms of the limit, we just also plug things together. We can also look just at what was the value of the tangents, because right now x2 is equal to x1 plus delta. So we just basically put a limit here, and we have that. And then, because right now we don't really have this what we call singular. I think it's kind of I don't know how it's called in English, like singularity in the sense that we don't divide by 0. So here we can just say that delta goes to 0. So if you have a limit like this, like if you have that, and there's no singularity, so you don't divide by 0, no multiply by infinity, you can just say that, okay, the delta will be 0. And we get that the derivative of the function of quadratic function at point x1 is just 2x1. It would be the same as saying that x2 is just equal to x1, right? So it would correspond to this intuition of collapsing the 2 point in 1 point. Let me just, before carry on, I will just look at the chat. Okay, so nothing in the chat yet. So right now, so I told you I gave you some information about functions, what function changes. But the question, why do we even care about it? Like, okay, Alex, thanks for describing to us all this mathematical concept, but why do we need that? So there are a few very cool properties of the functions. So of the derivative for the functions. So if here I just draw in the blue line the function. So on the left it's quadratic, as we've seen, x squared. On the right is basically inverted quadratic. So it's minus x squared. In the orange, I just draw the derivative, because you remember derivative is also a function. It depends on 1 point. So you can just draw it as well. And look at this green points. You see that the derivative here is 0. It's not 0 anywhere else, but it's 0 here. it's a bit strange. Why is it the case? So let's look at this again, at these two graphs. And remember that the derivative is actually a tangent of alpha between the tangent, so the line which is kind of perpendicular to your, parallel to your graph, the current point. So if I just draw this tangent, and the angle is actually, so the angle is calculated between this line and the x-axis, right? So the tangent of 0, which is the angle, is also 0. So we have that at these points, we have the derivative is 0. But what are these points in this graph? So on the left is basically the minimum. So the function grows, and at x is equal to 0, it gets its minimum value, and the derivative is 0 here. And the same here. So here it's the maximum. So in the maximum, the derivative also is 0. It's actually kind of not only one situation, not only these two situations which can happen. There could be a third situation, which is called inflection point. It's kind of, it's where derivative is 0, but it's not a minimum nor a maximum. But we know that if the x is minimum or maximum, then derivative is 0 for sure. So it's kind of cool. It means that, if you know the derivative, you can say something about, the point and the function behavior at this point. But, if we just look at these functions, which look like that, the derivative here is 0. And it will always correspond to the minimum. So these functions are called convex functions. And in this case, you basically always have this nice property. And okay, so we can say, Alex, thanks for giving us this information, but why do we need that at all? But remember this regression problem, which we looked at the beginning. Here you have minimization. So you want to know the minimum of that. It's a function. So if you just look at this object, it depends of xi and yi, but these are kind of constant because they're given by the data set. They don't change really. What changes here, what you can change as a user, as a machine learner, you can just consider different functions. And you basically can think about it as like finding functions. So you look at that and you can say, all right, we know that if this is a convex, so if this looks like that, then if I just find the gradient and it's 0, then it's the minimum. So you should only care about the points, so the functions where the gradient of this will be 0. So it should be your reflex, basically, machine learning, generally speaking. If you know that your problem is convex, so it looks like that, then just focus on finding the gradient. So this is kind of cool, cool property. Let me look at the chat. Okay, I see 18 minutes to finalize. Sure. So let me just quickly say just how does the convex function how is the convex function defined? So the definition in the Wikipedia you can read. I think if you just read that, it may look a bit complicated, but let me just show you quickly what it means. It basically, we take any 2 points, we take the values of these 2 points, and we find a point which is in between these 2 points. And we look at this value of the function at this point, and we also draw a line between f of x1 and f of x2. And what convexity means is basically the value of the function in this point here, t, xt, will always be smaller than the value which is given by this line. So basically, it means that within the graph of your function, you can always fit a line which value will be larger than the value of the function. So it's true, you see, for if you take any x, the value on the line is always bigger. So just, this is like a definition. There are ways to understand whether a function is convex, but we don't really have time to go for it. Let me just show you the functions which actually are not convex. So this is not a convex function because it's kind of the opposite. Here you have a line which has a smaller value than the value of the function, because the value here will be bigger than this line. And here it's not a convex function, not a function like that, because you can have, like, if you look at the value, like at points here and here, and take any intermediate point here, you don't really have a situation where your function is always smaller than this line or always bigger than this line. So this is not a convex function nor a concave. What we call a concave function, this is concave function. It's kind of the opposite of a convex. So these are bad functions to work with in machine learning because we don't have this property that the gradient is gives you the minimum. All right, now let's try to put it in practice. So let's look again at the regression problem. Let's try to make use of the gradient. So we look at this regression, so at this objective, and we'll consider only linear functions. So the functions which we basically for xi gives you a times xi. So the problem above will be transformed to the problem here. Then we define g of a. So just the function which is defined by this sum expression. So right now we are minimizing over a, and we basically need to find a minimum of a function g of a, where a is a parameter and g depends on the data. So we know, like from what I've said above, that if this j is convex, then we just find the gradient, or we calculate the gradient of the function. We find where the gradient is 0, and then we are basically done, because there it will give us a minimum of the function. So is this problem convex? I will say, because we didn't go through all the steps on convexity, let me just quickly say that this is convex. It's a linear function, so just believe me that this is convex. This is a quadratic function, basically, as a function of a. So you remember the quadratic, so quadratic was convex. And also the sum of the convex function is also a convex function. Here we have a sum. We have a sum of convex functions. So g of a is a convex function of a. So it means that we can just find the gradient of g, put it to 0, and we are done. Let's right now try to understand how to use it. So here comes the gradient descent. So remember, so right now we are looking only in the convex functions, which have this property. So what are our options? We can either just find the derivative of the function, but it can be hard because if we want to analyze the derivative, it depends on the data. It can be a very hard function to analyze. Or we can, instead of just analyzing the derivative, we can actually change, like if we are somewhere here on the function, we can just change the x, and we kind of try to put the x and move it to the minimum. So this is kind of the approach we'll take for the gradient descent. In particular, what we will do, so just before that, at any point on the graph, the gradient will point to the ascent of the function. If the gradient points to the ascent of the function, the negative of the gradient points to to where the function decreases in value. This is true for the convex functions. So the gradient descent will work as following. We take some point x0, any point on your function, You calculate the gradient at this function at this point. You move to a new point. You basically move to the new point x1 by decreasing x0 by the gradient, and you also multiply it by small parameter beta, and you kind of repeat this process till things don't move. We call it convergence. If you just want to write it down, the algorithm, it will be written like that. So it will xn minus 1 minus beta times the gradient and the previous point. And just to note why it would actually at some point converge, because, you know, if you move here, if things are okay, if they're correct, you know, you always, because you're moving in the direction of decrease of the function, the value of the function will decrease, right? Because, and your gradient will decrease as well. So if you just apply this procedure, your gradient decreases, and if it goes to the minimum, the gradient will be 0. So it's kind of a nice way to have this adaptive algorithm, which you don't need to worry about. You just, you know, run it for a very long time, and at some point it will stop moving. And it will stop moving because it actually found the minimum. Or the gradient is very small, it's like around the minimum. I mean, under some conditions, it will be true. You know, if you think about the gradient descent, you need to just think about a few practical considerations. This beta parameter has to be chosen wisely. So if you make it very small, your like updates will be like very slow, and you may wait too much time for things to move to 0. But if beta is too large, you're risking actually skipping out the minimum at all, because, you know, you will move too much on the, you know, in this direction. So in practice, what you need to worry about, you just, you know, try different betas and choose the one which works well on your problem. Okay, so if we look at the gradient descent for regression, so remember we had this function g, which we try to find the minimum of. We apply the gradient descent to this problem. But actually, just, you know, to say this function g and the gradient of g depends on the whole data. And if your data is very big, so if you take, say, ImageNet, it's a quite a big data set, you'll have to calculate the gradient on the whole data set. This is kind of, you know, too much to calculate. And you have to do it every time you move. So it's like a lot of calculations. So right now, we'll look at the algorithm which is called stochastic gradient descent, which is actually, like, just if you look at these pictures, it's very simple. Basically, instead of looking at the whole data, you'll look at the subset of the data. So in the function will be defined on the subset of the data is just like, you know, the average of these differences, or not where E goes from 1 to N, but E goes from 1 to B. And you have the tildes here. And so B is called the batch size, and the tildes are basically, you randomly select the point. So the way you do in practice, you have your data set, which is extremely big. You close the eyes, you put a hand in your data set. You take a point, and you do it multiple times. So with replacement, it means like you actually take a copy of the point. So you still can pick the same point multiple times with some, you know, random probability. And then you just construct this batch, which will be quite a small number compared to N. And then you calculate the gradient there, because it's a smaller subset, it's cheaper to calculate. And then you can apply this procedure, which is quite cool. So basically, if you just look schematically, how do they compare? It's just, they compare in just 2 steps. So first step is just you need to randomly select this subset at every iteration. And then the gradient is just calculated in a smaller subset rather than on the whole data set. And one trick why this thing is actually very cool to apply this, you know, this algorithm in practice is because we know that the sum of derivative is so derivative of the sum is the sum of derivatives, and the gradient, can be actually written as the sum of terms because it's just the sum of these terms, right? And if you just take the gradient of that, it will be just the sum of gradients. So what you can do in practice on your machine, you can actually calculate the gradient for every term in parallel. So if you have, like, say, B machines, you can just calculate all those things at the same time and then just, sum them over, which is basically what happens on GPUs. Voila. So this is why the stochastic gradient descent works quite well generally, because it's easy to parallelize and it's kind of cheap to calculate. But obviously, because you calculate it on a subset of the data and not on the whole data, you introduce some error, but which is mainly a kind of is called the variance. And I don't really have time to speak about what is the variance and how to get rid of it. But generally, if you increase the the number of points you consider, if it's closer to the to be a full data set, then the variance will decrease. All right. So just to say, the gradient descent is an algorithm which finds the minimum of the convex function. That's why knowing the gradient of your function is important, and that's why also knowing whether your function is convex is important. Obviously, for like regression and actual problems, you would use stochastic gradient descent, which is a cheap version of doing gradient descent. But actually, a lot of deep learning problems are non-convex, but we still apply gradient descent, and it still works quite well. It's not yet clear why it is the case. But in general, if you don't care only about machine learning, but any other optimization problem where you have to find the minimum, it may not be a very good algorithm if it's not a convex function. All right, so let me just put my contacts. If you have questions after the talk, or just want to reach out, just feel free to to write me an email. Just say that you were in this talk, so I know how to refer. And let me look at the chat. Okay. Okay, so I try to open the Q&A.
There's a question on the QA, Alex.
I can't see any. I can't see questions for some reason.
Yeah, you should be able to see just on the downer bar. You should be able to scroll and you see QA.
Yeah, I see the QA, but I don't see the question. Like, for some reason, it doesn't pop up. Let me see. Can you maybe read the question for me?
Yeah. Is there
sorry, I see it.
Okay, perfect.
Okay, the question is there any algorithm method to help in selecting the optimal parameter of beta in gradient descent, or it's basically trying different values until it works? So actually, if you look at the stochastic gradient descent, there is a theoretical, there is a theory of what kind of learning rate it's called. This parameter beta is called learning rate, which you have to choose. Basically, like in theory, you have to decrease this parameter over time. It has to be very large at the beginning, and then it needs to start to decrease when you do more and more iterations. However, in practice, if you start to decrease it in the way which is suggested by theory, it will be too small. And also, it's true for convex problems, but generally, if you work with deep learning, the problems are not convex. So the gradient descent should not work a priori, but it works. So there, the best way to do is just to try different values. What people also do in practice, they do the schedule. So you kind of still decrease it a bit over time, but not too much. It doesn't go it should go to zero, generally speaking, but, not too slow, go to zero. But, you don't decrease it to zero, but by a much smaller value from which you started. And there are also some algorithms, like either evolutionary algorithms, which basically try to adjust this alpha parameter on the fly. What they do is that you fix some parameter beta, sorry. You run your algorithm for a few iterations, and if it improves well, you kind of fix this value and you say it's a good value, and you do it in parallel multiple times. You run multiple algorithms at the same time. You look at the values, and then you say, okay, which one is the promising candidate? Like, you know, in evolution, you select the promising candidate, and then you take the beta, which was kind of worked well, and you mutate it. So you randomly perturb it. So you just add, you know, move it a bit, and then you try it again. And when you run this algorithm, it just changes during the learning. So this is called evolutionary algorithm. Okay, so I see that it's already 8. If you have any questions, let me just write my email here. Just feel free to reach out. I will share the slides. Yeah, I mean, learning rate has to be small. Like, it can be more than 1. It depends on the gradient. But you know, so if the gradient is very, very small, like, you know, 0.0000001, then, you know, you can even put the learning rate more than 1. But, you know, generally speaking, you know, in practice, what we see that it's like the gradients are not very big, like not very small neither. So you kind of put it to some small value, 0.1 or 0.001, and you just try multiple of them. And, you know, in theory, still there is a theory which says that learning rate has to go to 0. But, you know, in practice, so it's have to be small, like ideally have to be small. But, you know, theory works until the assumptions of the theory are true, which they are not always true.
Okay. Thank you very much, Mr. Alex. I've given you a round of applause, though you cannot